Hello, so today we are going to do this problem, which is part of Leetcode January Daily Challenge. So we get an array of strings words that don't have duplicates. This is important. And we want to return all the concatenated words in the list of words. Now, what do they mean by concatenated words? They mean that if it's comprised of entirely of at least two shorter words from this words list. Okay, so basically a concatenated word is a word from this list that can be obtained by concatenating at least two other words, right? You can concatenate more than two, but a 2 plus. Okay, and of course, like if you concatenate just one, that would be the initial string itself. So that's what it means here. So if we take a look at this first example, you can see, for example, this we have here cats, dog, and cats, and that's just a combination of cats and dog. So it's 2 plus, right? It's 2, and then it's a concatenation of them entirely. Like there isn't, if there was an x in the end, this word would not be a concatenated word because it's not entirely comprised of concatenated strings from this list. Okay. So if we take a look here, so there is this one which is comprised of cats, dog, and cats, right? And then there is this one that has dog, cats, dog, so still 2 here. And then this one has rat, cat, dog, cat. So it has this one, has this one, and then has dog, right? So it has even 3. So you get the idea. Now, in terms of constraint here, we have the list of words can be really big, 10 to the power of 4. The length of the individual words is a little bit on the smaller side, so it's 30. And so the words are unique. This piece is also important. So let's see how we can solve it. Okay, so how do we solve this? So this is an example of the first example we have. We have cat, cats, and then the rest. And so how can we think about this in a way that we can arrive at a solution? So one way to think about it is, let's pick, for example, one of the words. Let's pick the bigger one, right? What do we want to do? We want to be able to get from a letter, the first letter, to the end using only other words from the list, right? That's exactly what we want. Okay. And so that means we want, if we try to think of it in terms of a graph, that just means we want a path from index 0 to index n-1. And what are the edges? So if you want a path and you want to use a graph, then we need to think about what are the edges. Well, what are the components of this word here? Just letters, right? And their indices, right? And here you can see, if we want to term it in terms of a graph, a path is usually from a source node, right, to a source destination. So this all tells us maybe we should try to make the letters be the nodes, because we go from one letter to the other, and that's the path we want. So okay, so that means maybe let's have a graph for each word. So basically this is for a specific word that we want to check if it's a concatenated word. So for each word, what we can do is just create suppose we have a graph out of that word, and the nodes are basically the letters. Of course, we'll represent them with their indices. And then what would be the edges now? That's the question. Well, let's think about what would be the solution. You can't divide this into just CA and then TS. Why is that? Because there is no CA and TS in Word, right? And so the edges have to be just from the valid transitions. What are the valid transitions? The valid transitions is if it's a word in this list of words, right? So for example, from a C to a T, that's a valid edge, right? And so what we can say here, for example, this is a valid edge, right? Let me actually write it in a different color. So what we can say for this one here is that C to T, this is a valid edge. C to TS is a valid edge here. Dog, D to J here is a valid one, and here C cat is a valid one, and this is a valid one. So we can create edges like this. Because why is that? Because the path that we want to take, that we want to end up with, has to be just something like cat. Here it's not cat possible, but here the correct path would be to get to the end is going to be cat to dog, right? To cats, right? And by the path I mean you go from C to S, you go from D to J, and then you go from C to S, right? And so that's exactly the idea here, is that let's just make this be a graph, and we can just, how can we find if there is a path from one node to the other in a graph? Well, we can just use DFS, right? And this is the smart idea, is that, well, there is no edge between C and A because there is no word CA in this word, in the list of words that we are taking a look at, okay? And so with that idea, we can just solve our problem, right? We would have an implicit graph that basically says if, let me write this down. So if Wij is in the words, and maybe we can convert it to a set so that it's easy to check, then that means basically there is a path, there is an edge from I to J. Okay, so that's the main idea here that we are going to apply. Now there is one caveat though. So from this C, what about from this C here to the last S, right? For this word. If there is a path, should we say this is a concatenated word? Well, no, because the problem says at least 2, right? And it needs to be different words, not the word itself, right? And so, but this is a word in the list of words, so it is a valid edge according to our graph definition. So how do we avoid that? Well, we can just do the check. When we are doing the traversal to find the path, we can just make sure that either I is different than 0, or J is different than N, just so that we don't count this edge, right? So for each word, we don't want to count the edge that constitute the word itself, right? So that's the only distinction. But otherwise, the rest should be the same. Okay, so let's take a look maybe at the second example and apply it there. So the second example is cat, dog, and then cat, dog, right? So what we will do is we'll run through the example. So first, cat. Okay, and we'll just say do a DFS for I. So I will start here, and we'll check for all J's, right, that are from I here. So I'll say, is C, so is the Wij here, is this a valid edge? Is I to J a valid edge? Well, it's not, because there is no C in the list of words, right? This is not in the list of words. So it's not a valid edge, and so we move our J here. Is CA, which is Wij, a valid edge? No, it's not, right? So we move J again. Is T a valid, is I to T a valid, C to T here, which is I to J, a valid word? Yes, it is, right? But the problem is that I is equal to 0 and J is equal to the end of the string, and so this is not the edge we should take, because it's the word itself, and so this one would fail this check here. Okay, and so we would not count this. We'll not add it to our result, so our result is still empty. And then we move I. So we move I. We want to try all substrings. Do we move I? No, we wanna get the entire path, so we don't move I. So we try the next word, which is dog, and so now I is here, J is here, same thing. D is not a valid edge. We move J. Is Do a valid edge? It's not in the string, so it's not valid. We move J. Is dog a valid edge? Yes, but it fails this condition because this is the word itself, so we don't use it. And now where it becomes interesting is now we look at cat, dog. Okay, So I starts here, j starts here, we move because CA is not a valid edge, cat is a valid edge. So this is where it becomes interesting. So cat is a valid edge, and it passes this condition. So it's different than, I is different than I is equal to 0, right? But j is smaller than n. So this one is valid for this condition. And so that means we need to add to our result, we need to go next, right? So this means basically this is a valid portion, and so we advance our I here. Just DFS, right? We found the first edge, and now we want to continue our path to find a path to the end. So I becomes here, j is here, we move j here. Now we have DO not in the list. We move j here, dog is in the list, and I is different than 0. And so this is a valid edge, right? And then when we reach the end, n-1 here, or you can say end because we will increment. When we reach the end, that means we are done, right? And we are done, and there was a path. And so we'll say that this is a valid concatenated word, and we'll add it to the list. I hope that made sense. I think it will be even more clear with the implementation, but essentially we are creating a graph where for each word, we'll go through each word in the list, and to check if it's a concatenated word, we will have an implicit graph where the nodes are the letters and the edges are the constructed using the words in the list. So there is an edge if from I to J if W from I to J is in the list of words, right? And you want to find a path using DFS from 0 to the end of the string word, such that there are words in between, right? It's not just 0 to n-1. We want words in between because that's what the problem says. It's at least 2 words, at least constructed from at least 2 words, right? So that's what we want. So that's the idea. And so graph, nodes are the letters, edges are based on the words in the list, and we do DFS. Pretty straightforward. So let's implement it and make sure it passes our test cases. Okay, so let's implement the solution we just saw in the overview. So what we need to do here is so first we need to do our word set, right? And so this is going to be a set of words. And then we need to go through each word, right? So this is just to easily be able to check if a substring, right, from I to J is part of the list of words, because that's exactly what determines if there is an edge or not, okay? So here we'll just go through the list of words. And the second step is to, of course, do DFS, as we said, for that word, and we'll start at 0, because remember, our nodes are the letters indices, and this is the starting node. And we want to check if there is a path to n-1. So this checks if there is a path from 0 to n-1 in graph of words set, right? And so that's exactly what we need here, is to define a DFS function that is W word is fixed, and then I is just the node that we will traverse, okay? And of course, for DFS, we need a visited set, and we start out with just 0 because that's what we pass here. And then when do we end? We end when we reach the end of the string, right? And so let's define the end of the string. It's just the length of word. And if we get here, that means we are good. And so we want to add this word, because this means basically we found a path, right? So this means we found a path from 0 to n-1 using, or n the end, right? Using words from word set. Okay. Of course, it's not the word itself. It's not the word itself. That's something we'll pay attention to. We'll take care of it, down the road. And so here, this means we want to add it to the list of results, right? Because it's a valid one. Basically, if we find a path, that means it's a concatenated word. So here, we'll just need to define the list that we want to return that gets filled by DFS. And so here, we just return that list. And now let's define the core of our DFS here. So what we need to do is we need to check if there is a path from I to J. If there is an edge like this, then that means let's consider this one a portion of the path, and then let's check if there is a path from J to N, right? Because we found a path from I to J, and so to find if there is a path from I to N, we just need to find if there is a path from J to N, and this can be, by the way, multiple steps, right? It doesn't have to be like direct edge, right? We can have multiple other steps in between. So here, we just want to try all of them, right? So so we want to try all the, let's say we have cat, dog, right? What we did is we tried this C to see if it's a valid edge from 0 to 0, and then we tried CA to see if it's a valid edge, and then we tried CAT, right? So each time we try a different J and check if there is an edge. If there is an edge, then we continue from J. And so here, that means we will go, we'll do exactly that. And we will say, so we need to go to I because we want to check the letter itself. And I'm doing n+1 here just because of Python to get the entire, let's say we are here, we want to get the entire string. And so how do we check if it's an edge? Well, we just check if it's part of the words set here. So if this means this is a word. But we need to safeguard against just taking the entire word. So how do we do that? We just check that either I is bigger than 0, which means it's something like this, so it's not the entire word, or J is not the end, which means it's maybe something like this, or something like this to the beginning, or something like this to the beginning, right? And so we check J different than the end, okay? But we also want to make sure it's not visited. We don't want to visit the same nodes twice. That's just general DFS logic, right? And so to do that, we want to check here and J not visited. Okay, so if all of these are correct, then we want to add it to the list of visited, of course, but we want to also call DFS and proceed and check if there is a path from J to N. Okay, if there is a path, we'll reach here and we'll add the word, and so the word would be the path will contain W from I to J, and then some other path from J to N. Okay, and that's pretty much it here. Pretty straightforward once you get the idea of using the letters as nodes, and the words here as edges. And so if we submit this, and that passes our test cases, right? You could of course do this DFS in an iterative way, and I think that solution is a little bit easier to work with first. So yeah, as an exercise for you, try to do it with iterative DFS. But yeah, I think that's pretty much it for this problem. Please like and subscribe, and consider supporting me on Patreon, and see you on the next one. Bye.